Welcome everyone. I will be making a series of lectures in which I will be covering the topic crystal plasticity. So in the first lecture, let's have a look at the basics of crystal plasticity. So crystal plasticity, what does the name suggest? It is made of two words, crystal and plasticity. Now, as we all know, crystal is a solid material with atoms in an orderly arrangement, like BCC, FCC, or SCP. In these, all the all three cases, the atoms are arranged in a particular manner and are solid in nature. So that is crystal. And plasticity, the plastic deformation, ability of a material to undergo permanent deformation, that is beyond the elastic limit. Now, if we look at the microstructural aspects of deformation and damage nucleation, then suppose we have a component, okay, and a component has various macrostructures, as we can see. If we took one macrostructure and then zoom in, then it has various microstructures. If we zoom in one area, we can see the microstructure, and it has then atomistic scales also. We can see like the boundary structure, the vacancies, the twin boundaries, the boundary dislocation. So if we can improve the properties here or here, let's say, then the microstructure properties will be improved. What does it mean by properties getting improved? It means that toughness or the ductility or the hardness is getting improved as per the requirement of the component, and hence if this is getting improved, then the component is getting also enhanced. So it is important to understand this aspect, and for that crystal plasticity plays a very important role. So this is a kind of a future thing which we will discuss in the subsequent videos, that why I just wanted to show you that why crystal plasticity understanding is important. Then if we look at the plastic deformation at the microscopic level, then it can happen only due to the shear stresses. The normal stresses can only contribute to the elastic deformation, but it cannot permanently change the arrangement of atoms which is required for plastic deformation. If we try to understand from the schematic that this is the initial configuration, and under the tension and compression these kind of things are happening, but no permanent shearing of atoms is happening, which is required for plastic deformation, which happens only under shear. And this is also stable kind of, I have written unstable and stable, because this is for simplified for visualization. This much gap is will not be there, only between the blue and the red atoms. The gaps will be here also, and this is not stable because the atoms would like to be in the initial stable configuration, because it was initially present there without any force or energy being acted. So if we remove it, that is why it causes elastic deformation. But if we look at the shear deformation, like if we pick this set of atoms, it is just looking like the initial one. That is why it is called the stable deformation. The stable arrangement of atoms is again being achieved. So normal stresses can affect the volume or shape elastically, but does not provide the driving force for dislocation movement, which is required for plastic deformation. And only shear stress can cause atoms to slide past each other and create permanent changes. But then how during a tensile test the material undergoes plastic deformation? How does that happen? So there comes the concept of resolved shear stress. Now this is our tensile loading direction, and this is our area which is acting normal to the which is normal to the our tensile force direction or tensile loading direction. But our slip systems, that is a combination of slip plane and slip direction, may not be aligned to that area which is normal to the tensile direction. It may be at some angle. So we calculate the slip plane area, that is A by cos phi. And similarly, the resolved force on this slip plane will be F cos lambda. So if we calculate the resolved stress, it gets F by A cos lambda cos phi, where cos lambda cos phi is the schemic factor which depends on the as we can see on the orientation of the stress axis with respect to the slip system. Now, for will this year's the plastic deformation will happen for any resolved shear stress? The answer is no. It will happen at a critical value, and that is called critical resolved shear stress. And Schmid has experimentally shown that the slip of a crystal on its slip plane requires a critical stress, shear stress, that is tau c. And if tau is less than tau c, no plastic deformation. And if tau is greater than tau c, not possible. At tau equal to tau c, when tau reaches tau c, the critical resolve stress is achieved, and hence the plastic deformation occurs. Now, if we try to carry out that tensile test without constraining the ends, then the ends will move relative to each other, and this kind of scenario will achieve. But in a real test, the ends are constrained. So the slip direction moves towards the or away from the tensile axis, and will and when this happens, like suppose at first this slip a particular system is active, but when the slip systems uh, start getting rotated, uh, as the tensile test is continued, then other slip systems may get more favorable cos phi cos lambda values, and they might reach also tau c for that slip system, and hence that slip system can also get activated. Similarly, multiple slip systems can get activated. As we know, there are multiple slip systems. In HCP there are 6 close pack slip systems. In BCC there are 48 slip systems, and in FCC there are 12 slip systems. So it's not that only one slip plane and one slip direction is getting activated. At first it might happen then only one is activated, but eventually as the test is progressed, multiple slip systems can get activated, which can cause multiple slip. So in this video up till here only. In the next video we will see how to determine those slip systems which are getting activated, those multiple slip systems, and we'll see the introduction to CPFM, that is crystal plasticity finite element method. Thank you.